This is another question based on Malus law. So let me write the question. In the figure given below, so we will draw the figure. In the figure, suppose that the transmission axes of the left and right polarizers are perpendicular to each other, let the central polarizer be rotated on the common axis with angular speed of omega. Show that if unpolarized light beam is incident on the left polarizer, with intensity I max, then the intensity of the beam emerging from the right disc is given as follows. So let me first draw the diagram to make things clear. So we have a polarizer. So let us say this is the transmission axis. Then we have another polarizer whose transmission axis is perpendicular. So perpendicular, this is the transmission axis. Then we have a polarizer in the middle of these two, for this polarizer the transmission axis is somewhere over here, and this transmission axis is rotating. So this polarizer is being rotated by omega. So the transmission axis is also rotating by that angular speed. So this is the left polarizer, this is the right polarizer, this is the central polarizer. We have incoming incident light beam with intensity I max, and we want to find out the emerging beam's intensity. And we want to show that this I is related to I max and omega by this kind of a relation. And these two polarizers, the left one and the right one, the transmission axes for them are orthogonal to each other. So let us start solving the question. Since we have unpolarized light coming in, so after the first polarizer, let us call this first, let us call this second, and let us call this third. So since unpolarized light is incident on the first polarizer, so after the first polarizer, the intensity is going to be I max over 2. Since unpolarized light is incident, this is important to start with. Then after the second polarizer, now here we will use Malus law. For the second polarizer, the incident beam is this one coming after the first one. So here intensity is I max over 2. So after the second polarizer, we will have this intensity coming from Malus law. We saw Malus law in the previous video. So Malus law we can recap. So this is the diagram explaining Malus law. So Malus law states that if polarized light is incident on a polarizer whose transmission axis makes an angle theta with the incoming polarization direction, then the output intensity will be I naught cos squared theta, where I naught was the incoming intensity. So this is Malus law. This is what we are using here. So here incoming intensity is I max by 2 because it is after this first polarizer, and theta is the angle between the polarized light coming after the first polarizer and the transmission axis of this second polarizer. Now here we had unpolarized light incident on the first polarizer, but after the first polarizer the light would be polarized because the light would be polarized along the direction of the transmission axis of the first polarizer. So we have polarized light input on the second polarizer. So this is from Malus law. Then after third polarizer, again we will use Malus law here. So now this intensity is incoming intensity on the third one is I max by 2 cos squared theta. So after third polarizer we will have, this is the incoming intensity times cos squared of, now this will be 90 degrees minus theta. Why 90 degrees minus theta? Because let me draw a cross section of these polarizers. So the first polarizer has a transmission axis, let's say along this direction, and then the third polarizer is having perpendicular to the first one. So this is first, this is third, this angle is 90 degrees, and the second polarizer is having transmission axis direction somewhere in between. This angle we are calling theta. So this is second. So the angle between the transmission axis of the second and the third polarizers is going to be 90 degrees minus theta. So that's why we have 90 degrees minus theta over here. Now theta in our case is going to be omega t because theta is given by this angular speed. So this polarizer is being rotated by angular speed omega So the angle that it makes, theta, would be omega times t. Now let us use some trigonometry to simplify these expressions. So we will use the following trigonometric identities. Cos squared theta is like so, and similarly sin squared theta, and sin squared theta, basically this term right here is sin squared theta. So because we have cos squared 90 minus theta is essentially sin squared theta. So let us write down. So this is our final output intensity I. So let us simplify. Now we will plug in these trigonometric identities. Now 1 minus cos squared any angle is sin squared that angle. So this is going to be sin squared of 2 theta, and sin squared of 2 theta will again use this identity over here. So we will write it as follows. And theta is nothing but omega t. So that's that. And this solves the question for us. We have obtained the expression for intensity coming out of the third polarizer, and we have found this expression. This was what we were supposed to find. So we were given this setup of 3 polarizers. The first and the last polarizers had transmission axes orthogonal to each other, and the middle one was rotating with angular speed omega. So its transmission axis was also rotating with that same speed, and we were supposed to find out the intensity emerging from the last polarizer, given that completely unpolarized light beam is incident on the first polarizer. So we have repeatedly used Malus law over here, and also the fact that if unpolarized light beam is incident on a polarizer, then the output beam is polarized along the transmission axis of the polarizer, and its intensity is half of the input intensity. So this solves the question. This was another question based on Malus law.